Hey everybody. Today we're talking about moment-generating functions of continuous random variables. The basic definition is exactly the same as in the discrete case. The moment-generating function m of t is defined to be the expected value of e to the tx, where x is the random variable. And the moment-generating function is defined whenever this expectation is defined in a neighborhood of t equals 0. When x is continuous, the expectation is computed using a definite integral. So we're integrating over the support of the random variable x, call that support s, and then we integrate e to the tx times f of x dx, where f of x is the probability density function, the PDF of that random variable. Let's jump right in with an example. Compute the moment-generating function of an exponentially distributed random variable. That is, one that has density function f of x equals 1 over theta e to the negative x over theta, where theta is a parameter, it should be positive, and x, the random variable, has support x greater than 0. After we get the moment-generating function, we'll use it to compute the mean, variance, and standard deviation of a random variable with this distribution. As usual, I recommend pausing the video here, trying this on your own before seeing my solution. So we need to integrate e to the tx f of x over the support. And so that means integrating from 0 to infinity 1 over theta e to the tx e to the negative x over theta. That's an improper integral, so that means we're going to do a limit. We're going to let r go to infinity and integrate from 0 to r. We collect those exponential functions together, integrate with an antiderivative, plug in the endpoints, evaluate the limit, and overall we find that the limit converges to -1 when t is less than 1 over theta, and it diverges otherwise. So the moment-generating function for this random variable is 1 over 1 minus theta t, as long as t is less than 1 over theta. We then find the expected value of x as well as the expected value of x squared by computing m prime of 0 and m double prime of 0 respectively. And that's just your basic property of the moment-generating function. So we do out the derivative, we plug in 0 and we get theta. We do another derivative, we plug in 0, we get 2 theta squared. So remember, these derivatives are with respect to t. Now we can apply the formula for the variance of a random variable. The variance is equal to the expected value of x squared minus the expected value of x quantity squared. In this case, we get theta squared. So the standard deviation is theta. In a nutshell, both the mean and the standard deviation of a random variable with an exponential distribution are equal to the parameter theta. One more example. Find the moment-generating function of a normally distributed random variable, that is one with this density function, on all of the real numbers, and then use that MGF to verify the expected value of such a random variable as mu, and the variance is sigma squared. So it's another kind of nasty calculation. We're integrating e to the tx times the probability density function, this time over all of the real numbers. There's a lot of algebra that I'm not going to talk about. Basically what's going on here as you go from the top line to the second line is we're combining the exponential functions there, e to the tx, and the exponential, so e to the negative x minus theta squared over 2 sigma squared. After that, that exponential, the sort of exponent of the exponential, it has a square to be completed. Once we do that, we get a constant factor of e to the theta t, mu t, plus sigma squared t squared over 2. And then we get this integral of a thing that turns out to be the probability density function for a random variable with a normal distribution. And that means, since we're integrating a probability density function over the support, the integral has to be 1. Therefore, the moment-generating function is e to the mu t plus sigma squared t squared over 2. We differentiate that with respect to t and plug in 0, and we get mu. Differentiate it again with respect to t, plug in 0, get mu squared plus sigma squared. So that's the expected value of x squared. Once again, applying the formula, variance of x equals the expected value of x squared minus the expected value of x quantity squared. Doing a little bit of arithmetic and simplifying, we get that variance is sigma squared. So the mean and variance of a normal distribution are mu and sigma squared respectively, just as we'd hope.